movement, heat, light, sound, electricity, forms of energy, the ability to make things happen. The cars have energy because they're moving, movement energy. A moving car can make things happen, for instance, when it collides with another one. Energy is the ability to make things happen, to cook hot peas. The fire has energy because it's hot, heat energy. A fire can make things happen. It can make other things hot. Energy makes things happen. The children have energy because they're high up. We call it position or potential energy. A high position can make things happen. It makes children move fast. Wherever things are happening, wherever there is change, energy is involved. Life itself means energy. But for science, we must measure energy, and we can do so in different ways. The wheel moves against the force of friction, the force of the tight rope rubbing on it. To find the energy needed for each revolution, first we have to measure the force of friction. We measure the weight and the reading on the spring balance. Then in one revolution, the wheel moves against the force for this distance. We can measure that too. Force and distance, measurements needed for one way of calculating energy. To find how much energy is transferred to the water in 1 minute. We measure a temperature rise in a known mass of water, another way of calculating energy. To find how much energy this lamp takes, electrical energy measured in joules. But these units can be used for all forms of energy, heat, movement energy, and so on. Sometimes we use a larger unit, 1 million joules, called 1 megajoule. This car gets its energy from petrol. Chemical energy. The chemical energy stored in a gallon of petrol is 156 megajoules. The chemical energy in the petrol is being released. Some of it's changed into movement energy. And the engine is hot, so there's heat energy too. At 70 miles per hour, the movement energy is 500,000 joules. But when the car stops, what happens to that movement energy? We set a camera underneath our car to look at the brakes just inside the front wheel. The car was driven very fast. The driver braked, and our camera showed the brakes were getting hot. The car accelerated and braked a number of times to make the effect show clearly. Eventually, the brakes were red hot. So when the car brakes, movement energy changes into heat. Let's recap what happens. Some of the chemical energy in the fuel is changed into movement energy. At the same time, since the engine gets hot, some of it's changed into heat. Later, the movement energy is all turned into heat. But in all these changes, the total quantity of energy doesn't change. Energy isn't created or destroyed, and this is a fundamental law of science. Energy cannot be created or destroyed. In these changes, the overall change has been from chemical energy to heat energy. Even without a car, it's a change that's easy to bring about. It happens readily. But the opposite happens less readily. Without trick filming, things like this simply don't happen. So you can't so readily turn heat back into chemical energy. And that means all energy eventually ends up as heat and so becomes less available. Living needs energy, the energy we get from food. But comfortable living needs a lot more.
It's Radio 2.
And not only for heating, lighting, cooking, but also for manufacturing the things we use. Take a loaf of bread. Bread made from flour, made from wheat, grown on farms. Tractors need energy. Farmers use artificial fertilizers, made from ammonia. That needs energy. The combine harvester needs energy. The milling of wheat needs energy. So does baking. Even slicing. And transport. Altogether, 21 megajoules to make a loaf of bread. And just about everything in modern life needs energy to manufacture it. For a dishwasher, about 8,000 megajoules. For a house, it's about 600,000 megajoules. For a car, about 90,000 megajoules. So, in thinking about the energy a person needs, we must include all this energy needed for manufacturing things. And here's where it comes from, mainly from the chemical energy of coal, oil, and natural gas, the fossil fuels. These energy sources provide virtually all our needs. It's about 500 megajoules per person per day. And what we use and what we get from fossil fuels are just about equal. Now, over the next 20 years, we can expect our use of energy to grow. And it's likely that the supply from fossil fuels will be able to grow too. But maybe not fast enough. Many people say there's going to be a gap. To fill that gap, we hope to have a completely different source of energy, uranium. Nuclear energy. Electricity generating stations using nuclear energy are already meeting about 3% of our energy needs. But the development of nuclear energy is meeting with many snags, and it may not be a complete answer for the future. And supplies of uranium, like supplies of fossil fuels, are limited to what planet Earth can provide. As supplies dwindle, all these sources of energy will get much more expensive. So where else can we look? The sun, perhaps, already providing heat and light for us and for growing crops. Could we use it more? The movement energy of waves. Today, scientists and engineers are exploring many alternative sources. But we've time to look in detail at just one. The movement energy of wind. The details of a traditional corn grinding windmill will show not only how it works, but also the practical problems of using wind. The sails are angled so the wind doesn't meet them square on. This angle is called the pitch of the sails. Very strong winds might cause damage, so for safety, each sail is made of slats, which can open to let strong wind pass harmlessly through. A sail is an elaborate piece of machinery. At the back, the fantail keeps the main sails facing into the wind by driving round the entire top part of the mill whenever the wind changes direction. The movement transmitted by the slow rotation of the sails needs to be speeded up, so there are gears and shafts to bring down the energy from the top of the mill. A small amount of useful energy. But to get it, a windmill needs to be quite complicated. At Liverpool University, students are investigating wind energy using some modern wind turbines. They have a wind-making machine to be sure of a reliable wind for their experiments. Then a turbine placed in the wind stream picks up some of the wind's energy. They take measurements to find how much of the wind's energy can be picked up by different kinds of turbine. Their work illustrates some of the various patterns. The Cretan type with fabric sails is simple and relatively cheap to make. On the island of Crete, they use them for pumping water. The wind there blows mainly from the same direction, so these ones don't need a mechanism for making the sails face into the wind. With a similar design, this Norfolk commune are adopting the do-it-yourself approach to energy supplies. It's made from scaffold tube and bits of old cars. In America and in Britain too, this type has been used a lot for pumping. The large number of blades helps it to keep turning slowly against the heavy load of a pump. The vane helps to keep it facing the right way. An entirely different approach, the vertical axis turbine. This type doesn't need pointing into the wind at all, but this one is not very efficient. The National Research Council of Canada have a different vertical axis design which is much more efficient. It was planned as a cheap-to-build, easy-to-use pattern for use in developing countries. Like most modern designs, it's based on an aerofoil. This is a horizontal axis aerofoil with the shape something like an aeroplane wing. Depending on the exact shape, an aerofoil can be made to work best in strong winds or in light winds. This one works best in a strong wind and can go very fast indeed. That's an advantage when it comes to generating electricity. This aerofoil design is used to provide a standby lighting system in a London house. But the maximum output is enough for 200-watt bulbs. That's 200 joules per second. And that output is limited by the amount of wind which the blades can intercept. With future energy shortages in mind, we need to think on a larger scale. The blades of this machine have a diameter of 53 meters, and it produces enough electricity for 12,000 100-watt bulbs. The biggest wind turbine of all time. It was built in America in the 1940s, on a high hill where strong winds could be relied on. For a period, it generated electricity for the public supply. There are some interesting features. The blades are downwind of the tower. Here, the wind is from right to left. The pitch of the blades can be adjusted to keep the speed constant in a varying wind. But one night, disaster struck. One of the blades flew off. The turbine was immediately shut down, but they never repaired it. They reckoned that electricity from wind was 2 or 3 times more expensive than electricity made in other ways.